Alright, so we've seen a source coupled pair, the large signal characteristic, and we see that it's the output current is proportional to a square root of the input voltage. And so what we're going to look at now is, what if we, instead of using a resistive load, used an active load? And specifically, we're going to use a current mirror load. So let's look at the following circuit. We're going to make a PMOS current source, a current mirror, and we're going to tie it to an NMOS differential source coupled pair input. Rather than biasing this transistor with an ideal current source, we're going to use an NMOS current source that's just tied to a DC bias, setting up what our output current, or what our desired output current is. Alright, so this will be VI1, this will be VI2, and we'll have transistors M1, M2, M3, and M4. And what we'll say is that M1 is equal to M2 and M3 is equal to M4, so that we have symmetry along the center of the amplifier. Alright, so we know that our voltage gain takes a generic form. AV is equal to big GM times RT. And we're going to take our output from the drain node between M2 and M4. If you'll notice, one thing about this is that this is a differential input and we are only taking the output from one side of this amplifier, so it's a single-ended output. So one thing we can say about this particular amplifier is that it is an op-amp at this point, but it's not a good op-amp yet because the gain isn't going to be quite high enough and our output impedance conditions are not quite good enough. Okay, so now let's take a look at what our transconductance is for this device. So we assume M1 and M2 are equal, so we can say that whatever big GM1 is, it's going to equal GM2, since the same current's flowing through the devices and they'll see the same load. Now, we know that the generic form for GM, this is also a common source amplifier since we're taking the input on the gate and the output on the drain. So the generic form for GM for a common source amplifier is GM divided by 1 plus GM times whatever resistance we see in the source. Now in this case, the resistance that we see looking from the source of M1 is 1 over GM2. So this would be GM1 divided by 1 plus GM1 times 1 over GM2. Now we know that both devices are equal, so their GMs should both be equal. So we could say that this is GM1 divided by 1 plus 1, or GM1 divided by 2. So we can generically say GM1 is equal to GM2 is equal to GM over 2. Now the next thing that we need to find, obviously, is the output resistance at the output node. So if we put a test voltage source into the output node, Vx, and we measure the current flowing out of that test voltage source, we would find the output voltage, or the output resistance. Alright, so what we're going to find is an R down and an R up by doing this. Okay, so R looking down is equal to RO2 times 1 plus GM2 times the resistance connected in its source, which we see as a 1 over GM1. Again, knowing that these two are equal, we could say that R down is equal to RO2 times 2. Alright, now what's R up? R up is simply equal to RO4. So now let's find the current flowing into this node. So we'd find the current flowing into R down. We could say that IX is equal to VX divided by R down plus Vx divided by R up. But what we're going to find is when we cause a current to flow down through this device, because the current source here is a high impedance, all of the current that flows down through the device flows up through M1 and into the current mirror M3, which causes current to flow up. So we get another Vx over R down here. So when we solve for this, we find Ix is equal to 2Vx over R down plus Vx over R up. And when we make our substitutions for R down and R up, we find Ix is equal to Vx over RO2 plus Vx over RO4. The 2's cancel. And solving for this, we find that Vx over Ix is equal to RO2 in parallel with RO4. Now, before we realize that there is this current mirror action in this device, we might have guessed that the output resistance was RO2 over RO4. And we would have guessed correct, but it would have been for the wrong reason. So if we write our overall voltage gain for this device, it's equal to GM times RO2 in parallel with RO4. And I forgot to mention one thing. The reason that we have a single GM is that our output current, IO, is equal to GM times VI plus over 2, VI1 over 2 plus GM times VI2 over 2. Since the magnitude of the input voltages is equal, the swing is just opposite. We could say that this is equal to GM, I out is equal to GM times VI. In other words, our total GM is just equal to GM, not GM over 2. Another way of putting that is we can do superposition to find the total GM. Okay, so our total voltage gain is given by GM times RO2 in parallel with RO4. And we note that this is an op amp, but it's not a good op amp yet. Now, the last thing that we need to do is find the common mode voltage gain, and we will do that in the next set of slides.